Welcome to qnawire.
We have a biochemical reaction that takes place under these conditions. We have a 1 milliliter solution of 0.025 molar phosphate buffer with an initial pH of 7.35, and we have the following pKa's. We know that at pH equal to 7.35, the dominant reaction is going to be the one in the middle, so we don't need to take care of all of the other ones. What we know is that my buffer has an initial pH equal to 7.35. This buffer contains an amount of mole equal to a total amount of phosphates. I'm going to put it total phosphates equal to 0.025 molar, which is mole per liter, multiplied by the volume, which corresponds to 1 times 10 to the minus 3 mole liters. In this case, the total amount of phosphates that we're going to have in solution is going to be equal to 2.5 times 10 to the minus 5 mole. This is the total result that we can get. So in this case, since we know that the buffer is at pH equal to 7, and we have a buffer, we know that the pH is calculated according to the Henderson-Hasselbalch equation. So pH is going to be equal to pKa plus the logarithm of the concentration of the conjugate base, in this case, concentration of HPO4 to minus, divided by the concentration of H2PO4 minus. We can replace the concentrations by number of mole divided by volume because we know that the volume is going to stay the same. So amount of mole of HPO4 to minus divided by volume divided by amount of mole of H2PO4 minus divided by volume. Volume and volume cancels out, and we're going to arrive to an equation that is a little bit more simple to deal with. And that is going to be more useful when we add the acid mentioned on this question. So the pH will be equal to the pKa plus the logarithm of the amount of mole of HPO4 to minus divided by the amount of mole of H2PO4 minus. Okay, so now to know the initial values for amount of mole that we have, let's consider the reaction of H2PO4 minus that is going to generate HPO4 minus plus H3O plus. This is the reaction with water, of course, for this reagent. We're going to write down our ice table, where water is going to be neglected because it is a condensed phase and it is not going to enter the equilibrium equation. So we're going to put as initial value of amount of mole and total. Let's say that we initially have 0 and 0. The amount of change is the fraction that is going to be transformed into HPO4 minus plus x. And at equilibrium, we're going to get NT minus x, and x. So for this reaction, we know that the pKa is equal to 6.86. Thus, the Ka for this reaction is 10 to the minus 6.86. We can write down the value for Ka is equal to the concentration of HPO4 minus times the concentration of H3O plus divided by the concentration of H2PO4 minus. But since we already have the Henderson-Hasselbalch equation, what we're going to do is replace these values of HPO4 minus and Nt minus x into this equation over here. So our Henderson-Hasselbalch equation now reads that the pH is going to be equal to the pKa plus the logarithm of HPO4 to minus, we have a fraction of x divided by the amount of mole that we have of H2PO4 minus, which is number total minus x. So we can solve for x in this equation. The value for pH that is required initially is going to be 7.35. So 7.35 is going to be equal to 6.86 plus the logarithm of x divided by nt minus x. From this equation, what we get is that x divided by nt minus x is going to be equal to 10 to the 7.35 minus 6.86, which gives 10 to the 0.49. Rearranging this equation, x is going to be equal to 10 to the 0.49 times the amount total of mole that we had initially, minus 10 to the 0.49 times x. Thus, x times 1 plus 10 to the 0.49 is going to be equal to 10 to the 0.49 times nt. Finally, giving us a value for x equal to 10 to the 0.49 times my total amount of moles that we had, divided by 1 plus 10 to the 0.49. Replacing the value for nt that we calculated, that was equal to 2.5 times 10 to the minus 5, this value here, let me put it in red just to clarify it, red, it's going to give us, as the result for x, giving us a value of x equal to 1.8888 times 10 to the minus 5 mole. So now with this, we're going to know the initial values that we had of each of the compounds. This is equal to the amount of mole that we had of HPO4 minus, amount of mole of HPO4 minus, and the amount of mole that we have of H2PO4 is going to be equal to 2.5 times 10 to the minus 5 minus the answer, which is 6.112 times 10 to the minus 6 mole. Now we can proceed with what is going to be the pH after the addition of HCl. So we know that we added 3 micromole of HCl. HCl added is going to be equal to 3 micromole, which is 3 times 10 to the minus 6 mole. Now, the reaction that we need to take care of is the reaction of HPO4 minus plus H3O plus, that is going to generate H2PO4. Over here, it should be 2 minus. Sorry about that. Here I missed a minus, over here as well. So in here, we're going to have H2PO4 2 minus. Correct? And for this reaction, we're going to draw the same ice table in amount of mole that we had initially. So of HPO4 2 minus, the quantity that we have is equal to of the 2 minus ion, we're going to have 1.88 times 10 to the minus 5 mole. We're going to add 3 times 10 to the minus 6 mole of H3O plus, and we initially were going to have H2PO4 2 minus in a quantity equal to 6.112 times 10 to the minus 6. The amount of change is going to be minus 3 times 10 to the minus 6 mole, the limiting reagent, which is the acid that we added to the solution, and we're going to add that up over here. The result that we get is, at equilibrium, 1.588 times 10 to the minus 5 mole, 0, and 9.112 times 10 to the minus 6 mole. Going back into our Henderson-Hasselbalch equation, we know that the pH is equal to pKa plus logarithm of the derivation that we did earlier, the amount of mole of the conjugate base, that is HPO4 2 minus, divided by the amount of mole of H2PO4 minus. This is equal to 6.86 plus the logarithm, the amount of mole of HPO4 2 minus that we have is 1.588 times 10 to the minus 5, divided by 9.112 times 10 to the minus 6. The resulting pH is then equal to 7.1. As we were expecting, the addition of acid is going to turn our buffer, which was initially at a pH to 7.35, into something more acidic. In this case, into a solution of pH equal to 7.1. So this would be our final answer. Just as a recap, the first thing that we need to do is find the amount of mole that we have of each of the phosphate species, starting from the total phosphate amount that we had in solution. We did that employing the Henderson-Hasselbalch equation. We modified it a little bit to get rid of the volumes, to simplify our result, and get everything in terms of the amount of mole. With that, we got the value for x from this equation, solving, doing some algebra, finding that x was this value, 1.88 times 10 to the minus 5. The amount of H2PO4 to minus was the total amount minus x, as we saw here. And finally, with those initial quantities, we can proceed to add the 3 micromole of HCl to our solution to get the equilibrium amounts of mole and applying Henderson-Hasselbalch equation once more to get the final result. So that would be all. Thank you very much and have a good one.